Hey there, math team. As I told you, I was going to be making some videos to help us go through some more practice problems and expand what we've learned about some other concepts that may not have shown up during our practices, since we had to cancel a few of those. So what we're going to be going through in this series of videos, as you can see from up at the top, is the test that was given in 2020. You are currently working through the test that was given in 2021. We'll be taking a look at the 2022 one, some upcoming practices in person. So this one was going to be from 3 years ago, and in this video we're just going to go through the first 15 questions. Some of them that there's room on the paper, like on number 3 or number 4 where there's plenty of space, we'll just solve it straight on here, but on some of the others I may switch the papers back and forth. So just keep in mind, you can totally pause this and go back as many times as you need to kind of see the steps that we took to solve all of these problems. So let's go ahead and jump right into it. Number 1. A coin bank has 36 coins. Now that could be crucial. 4/9 of the coins are nickels. 1/6 of the coins are quarters. The remaining coins are dimes, and we're trying to figure out how much money is actually in the bank. So I'm going to grab a separate sheet of paper so I can show a little bit of work here. Now keep in mind, for the actual contest, none of the work actually gets collected. There's no partial credit. You either got it right or you didn't. So you should always remember, show as much work as you need to solve the problem. Beyond that, anything that you can do mentally, you should totally do it. So we've got 36 coins, and a good time saver is keep your abbreviations short. There's no reason to write out coins as long as you remember what you're talking about. And of those coins, we've got 4/9 of them that are nickels. So if I take that 4/9 of 36, that means 9 equal groups. So 36 divided by 9 is 4. So each group is 4, but I'm getting 4 of those groups. So 36 divided by 9 is 4 times the 4 that I've got here. That means I've got 16 nickels, and since it's asking for the total amount of money, I'm going to go ahead and convert that to cents. So I've got 80 cents in nickels. The problem also said 1/6 of the coins are quarters. Well, if we need 6 groups, going back to that original 36, we're not taking the 16 out because that 1/6 is of the whole group still. So 36 divided by 6 is 6. I get one of those groups, so that means I've got 6 quarters, which works out to $1.50. Now, it didn't give us a fraction for the dimes. We've got to figure that out. Now, I would imagine some people are probably going to end up losing a lot of time because they're going to try and figure out what fraction of that 36 coins the dimes are. Now, while it will work, it's going to take you a lot more time than is necessary to actually solve this problem. Because if we have 16 coins here and 6 coins here, that's 22 coins. There's only 36 total. So if I've already got 22 accounted for here, then I've got 14 of them left here. 36 minus the 22. So I know I've got 14 dimes, which gets me another $1.40. And then don't forget that very last step in the question, which is to add all of these values up. Well, with the 80 cents and $1.50, that would be $2.30, plus my $1.40 gets me my final answer of $3.70 for number 1. So let's go ahead now and move on to problem number 2. 24 students are members of the school choir. 1/6 of the choir is 3rd grade students. 5/12 of the choir is 4th grade students. The remaining members are 5th grade students. How many choir members are 5th graders? Now we're going to go back to the other page again. Give myself a little space to work down below that. This is a very similar problem to number 1, although I would say the difficulty is actually a little bit lower, because on number 1, not only did we have to figure out how many coins there were with that missing value for the dimes, we also had to figure out the total value. So there were a couple extra steps on top of finding the number of dimes. This one's a little bit more straightforward. We've just got to figure out how many 5th graders there are. We don't need to do anything beyond that. So if we have 24 total students, and from there it told us that 1/6 is 3rd graders. So we're just finding that fraction of a whole again, just like we did on the last one. And when you're finding a fraction of any whole number, the most simple and likely straightforward way to do it is divide it by the denominator, because that'll tell you how big each group is of those 6 groups, and then multiply it by the numerator because that's how many of those groups you get to keep. So if there's 24 students and there should be 6 equal groups, 24 divided by 6 is 4, so there's 4 in each group. I'm keeping one of those, so there's 4 third graders. Now it's also said 5/12 of the choir were from the 4th grade. Same kind of deal. There need to be 12 groups. We're keeping 5 of them. So 24 divided by 12 is 2, times the 5 means there are 10 4th graders. Now for the 5th graders, same kind of deal. Some people might go through and try and figure out the fraction here. If you're curious, it would be another 5/12, but that's not really going to help us that much. You're going to waste your time on that, because just like with the last one where I already had 22 coins, so I could just subtract that out from the total, same kind of thing going on here. We've got 14 students already accounted for. There have to be 24 total, so there's 10 5th graders. And that takes care of problem number 2. Always look for the most efficient path to the answer. They're not giving you bonus points for solving it in the most complicated way. So let's go ahead and move on now to problem number 3. This one we can just solve straight here on the paper. The table below shows the results of a race, and we've got Mackenzie, Kaysen, and Scott's times right here in decimals out to the thousandths place. To determine the winner, times are rounded to the nearest tenth, with the fastest time determining the winner, who won the race. Well, on this one, we just need to round it off to the nearest tenth, just to be absolutely certain we haven't had anything go a little bit weird. So if we're rounding to the nearest tenth, that's going to be that first decimal digit, so the 6 and a couple of 4s on the others. So 43.651, 651 thousandths. Well, if I'm rounding to the nearest tenth, I look to the right. That's a 5, so I'm going to round up. Mackenzie's time, if we're rounding that off to the nearest tenth, is going to be 43 7/10 seconds. For Kaysen, that 4, the 8's the next one, so again, I'm rounding that up, 43.5. Very close race if there's only a couple of tenths difference here. And then Scott, 43.44, so rounding to the nearest tenth. The digit to the right tells me to round down on that one, which means I'm going to leave this alone. We've got 43 4/10, so by just 1/10 of a second based on the official times, Scott would have been our winner on number 3. As we move on to number 4, what percent of the circle is shaded? Now, with a lot of questions that tend to pop up on these tests, you're probably going to want to deal with a fraction first. Easiest way to look at this one here, I've got 8 total sections. There's my denominator. 6 of them are shaded. Those are the ones we're worried about. And we could convert that to a percent from here. Got a couple of different options. There's a lot of ways you can solve these fraction to a percent problems. One of the best ways to do it is get it to a common fraction that you are familiar with. For example, 6/8. If I divide, whoops, not by 3, divide both of those by 2, I'm getting ahead of myself. 6 divided by 2 would be 3. 8 divided by 2 gets me 4. So this is the same value as 3/4, which I also know is 75%. If 1/4 is 25%, 3/4 would then be 75%. And speaking of some of those fractions, I told you there were a couple other ways you could do this. Another way is just do the division problem. If you take 6 divided by 8 and you add a couple extra decimal zeros on there and divide this thing out, guess what? You're going to get 75 hundredths, which equals 75%, because any decimal number, take that decimal, pop it 2 spots to the right, or multiply it by 100, you get your percent. The fastest way, however, and this is what we're going to do, we're going to add a little extra information out here on the margin, is just know some common fraction decimal equivalents. This would be something good to maybe write down on your own notes that we started with some of our in-person practices, or just watch this section multiple times, pause it, read it to yourself, and really learn these, because knowing some common decimal equivalents and how the fractions convert to decimals or percents can be super duper useful as a time saver. So let's go through some of these. We're just going to block off a section here, and we will have the fractions just as a generic A over B in one column. We will have the decimals in the next column and the percents in the third column. And the reason we're grouping all these together is because they are equivalent. I tell my class all the time, fractions, decimals, and percents are just the same numbers dressed up in different clothes. So here we go. 1/2 is the same as 5/10, which is 50%. 1/3 is kind of a weird one because it doesn't work out evenly. 1/3 is commonly written like this with that line above it. 1/3 is 3/10 repeating, which means it's 0.333333333 and it goes on forever, which works out to about 33.3%. Not exactly because the threes keep going, but it's pretty close, and a lot of times people will just kind of round that off to 33%. Another fraction you are going to want to be familiar with is the one that we just talked about, 1/4. That is 0.25, 25%. 1/5 is another one that's good to know. That's going to be 2/10, which is equivalent to 20%. Now 1/6, 1/7, there are decimals obviously for those in percents, but in terms of the ones that might be most useful to know are the ones that work out kind of evenly, except for 1/3. That one's just a fraction that pops up a lot. So let's just go ahead and jump to 1/8. This is one that maybe could have been useful to get to your 75%, just 3/4 would have been easier. 1/8 is 0.125, 125 thousandths. And when we take that decimal and do a little scooty 2 times to the right, that gets you 12.5%. Another one that can be kind of handy to know is 1/9. Even though this one doesn't work out evenly, it can be kind of useful for quick estimations and things like that. This one is 0.1 repeating, kind of like the 0.3 repeating from 1/3, which means we're going to get about 11 1/10%, or about 11%, just a teeny tiny bit more than that. The cool thing about ninths is that pattern continues, like 2/9 is 0.2 repeating, 3/9 is 0.3 repeating, 4/9 is 0.4 repeating, and so on. 1/10, that one should be the most obvious, matches up with 1/10, which is also 10%. So knowing some of those common fraction decimal equivalents can be a really great time saver, not just on the contest, but also just kind of simplifying a lot of other questions that might pop up, not just in 5th grade, but beyond into middle school, high school, and if you choose to pursue education beyond that into college. So let's move on now to, one other thing I almost forgot. Cool thing about knowing these unit fractions, once you know these, you know the rest of that denominator too. For example, if 1/4 is 25%, then 2/4, 2 of these, is 2 of these, 50%. And just like we saw over here, 3/4 is 75%, because if one of them is 25, 2 of them is 50, 3 of them is 75. Same thing with 1/5. If 1/5 is 20%, then you would know 4/5, 4 of these, is 80%. So again, great time saver for a lot of fractions. Let's keep things moving. Now we're going to actually use that skill. Write the percent that is equivalent to 21/30ths. Once again, several options on this. One way you could choose to do it is take that 21, divide it by 30, because that's all fractions are, just division problems. We could add that decimal and add however many zeros we need to do. I'm not going to do it that way because that's just going to be a huge time sink. It's going to take me too long to solve this problem when I have a better option. If it's not one of these common fractions, take a look at your denominator and check first to see, can I use equivalent fractions to get this to a 10 or to a 100? Because if you can get it to a 10 or a 100, tenths or hundredths, your decimal or percent, whatever you happen to need, is going to be a piece of cake. So with that 21/30ths, I immediately see, hey, I can divide both of these by 3. Keep telling you, these numbers are not accidental. They are very deliberately chosen. 30, if you divide that by 3, it gets you to a 10, and 21 is also divisible by 3. That gets us 7/10ths, which is going to be 70%. Because if I know 1/10 is 10%, then 7 of those is 70%. As we move on now to number 6, a circle has a diameter of 43 centimeters. What is the radius? Now we definitely need to know these two terms. Diameter is going all the way across the circle through the center. A radius is only going halfway across the circle through that center. Now the cool thing about these is the diameter is always twice as long as the radius. So you'll often see something like this. Diameter equals 2 times the radius. Now if we're going in the opposite direction, the radius is 1/2 the diameter. It's always going to be like that for a true circle. It's never going to change. It's just a mathematical constant. So if I know the diameter is 43, I need to cut that in half to get my radius. That means it's going to give me 21.5 or 21.5 centimeters. And that gets me my answer for number 6. So here we go, moving on. We're going to flip the page over, and let's take a look at number 7. So we're classifying triangles. We talked about this a little bit previously with another question, but as we go through and kind of talk about these things again, any triangle you ever see is going to have 2 acute angles. I don't care what kind of triangle you draw. I don't care how you try to draw it. 2 of those angles are always going to be acute, those less than 90 degrees. And the other thing I notice here is select all the correct names, which means more than one of these could be true. And as I look at acute, obtuse, and right, these are all classified by the angles. Equilateral, isosceles, and scalene, those are terms that are used to classify the triangle by its sides. So we'll just go through all 6 of these real quick and then determine which ones would be accurate. An acute triangle means 3 acute angles. Obtuse triangle means you've got 1 obtuse angle, the others are acute, because I just told you, always got 2 acute angles. Right triangle means there's a right angle. And then for the sides, equilateral means all 3 sides are congruent, exactly the same. Isosceles means at least 2 of them are congruent, at least 2 of them are the same. And then scalene means all 3 of them are different. So as I come back up and look at our triangle, it's been labeled with 5 inches, 7 inches, 10 inches. Those are clearly all different, so I know scalene is one of my correct answers there with F. Now as far as the angles, the one that I'm really looking at here is that large obtuse angle that goes further than 90 degrees. If you don't remember, 90 degrees is like the corner of a square or a rectangle. So that one's definitely obtuse. So B and F would have been the correct answers on number 7. For number 8, a regular octagon with side lengths of 12 centimeters has the same perimeter as an equilateral triangle. A lot of math and geometry vocab in there. What is the side length of the triangle? All right, well, I know an octagon has 8 sides. And if each of them is 12 centimeters, and we're talking about the perimeter, well, I could just do 12 centimeters times those 8 sides. That means it's got a perimeter of 96 centimeters. It also said that an equilateral triangle, I'll do my best to kind of make it equilateral, hey, for me that's not too bad, also has that same perimeter of 96 centimeters. But instead of the 8 sides of the octagon, we've only got 3 sides here. So if I take that perimeter, and equilateral means all 3 of them have to be the same. So if I divide that by 3, that's going to get me a side length of 32 centimeters for number 8. As we move on now to number 9, this one's one of the more straightforward problems on the entire test. It says the Pacers plan to increase the number of seats for fans. The additional section has 37 rows with 158 seats in each row. How many additional fans will be able to attend Pacer games? This one's just multiply. If we take that 158 times 37, now on this part of the test, you will not have access to a calculator, which would make this go a little bit faster. So you're just going to have to multiply this, but I trust in your ability to take care of that without too much trouble. You should have, when you go through that, ended up with 5,846 fans additionally getting into that game. Which, by the way, go watch a Pacer game. It's a delightful place to go see a basketball game. Go Pacers. Number 10, we had a problem like this on one that we covered in one of our in-person practices not too long ago. Cameron is wrapping loose coins to take to the bank. Nickels are packaged in groups of 40. Cameron has 3,320 nickels to package. Select all equations, so it could be multiple, that can find how many rolls are, that variable, of nickels Cameron can completely fill. So if he's dividing these up into smaller packages of 40, the first thing I'm looking for here is division. So I've got the total number of coins divided by 40 equals the R, how many rolls. So I know B is going to work. That one is 100% certain. Now, if you remember how we did the last one, it's the fact families that we want to look for. If I know something divided by 40 equals R, then R times 40 goes back to equaling that something. So D is my other correct answer on number 10, both B and D. And if you only put one of those, you will get it wrong. You got to make sure you find both of them if it's possibly asking for all correct answers. Now as we flip over to numero 11, number 11, a little Spanish with your math today. Joanna plans to make a quilt for her sister's birthday. She wants to purchase a minimum of 3 yards, so she's got to get at least 3 yards to get that discount. Joanna selects 4 different fabrics and purchases the following amounts of the first 3. So she's got 1 2/3 yards, half a yard, and 1/6 of a yard. What is the least amount of the 4th fabric she must purchase to receive the discount? Give your answer in simplest form. We'll come back to that simplest form in a bit because we won't need that until we actually find our answer. So on this question, we just basically need to take the 4 amounts, add them all up, and we need to get to at least 3. So the first thing I want to do is take the 3 values that I know and add those up. But the problem is 1 2/3 plus 1/2 plus 1/6. I can't add those because I have those different denominators. But if you remember how to deal with that, equivalent fractions are your key here. We can use equivalent fractions to change the denominators to something that does match. The first thing I always look for, can I get away with only changing some of them instead of all of them? Look for that smallest multiplication answer that you can get to with a 3, a 2, and a 6. 6 is our golden opportunity here. Because 3 times 2, 2 times 3, and leave the 6 alone. That's going to get us our equivalent fraction. So 1 2/3 becomes 1 4/6, plus the 1/2 becomes 3/6, and then the 1/6 just hanging out by itself doing its thing. So if I add all of these up, that gets me 1 8/6, which then is 2 2/6, because I can take 6 of those and make another whole group. So if I'm looking at this, again, don't worry about the simplest form until the very, very end. I've got to get to at least 3 yards. So if I'm already at 2 2/6, I just got to get another whole set out of this. So I need 4/6 of that last piece of fabric, but since it does say simplest form, I've got to divide both of those by 2, and she would need to buy 2/3 of a yard to get her discount on number 11. A lot going on there, but I promise the more time you spend getting comfortable with how to add and subtract fractions with different denominators, you'll find it becomes a very, 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 very handy strategy in middle school and high school. Number 12. The number line shows the fraction of a mile the track team runs each Monday through Friday to warm up. How many miles does each track member run in 2 weeks, which would be 10 days? Express your answer as a mixed number in simplest form again. Well, the first thing we've got to pay attention to is it doesn't really show us what fraction is going on here, but we do have the steps on the number line. So if I'm already at 0, and it's 1, 2, 3, 4, 5, 6 steps to get to the next whole number, that means my denominator is a 6. And it shows that each of these team members goes 1, 2, 3, 4, 5/6 of a mile to warm up. Well, if they're doing that for 10 days, that means it's a fairly straightforward problem of 5/6 times 10, which I know looks kind of complicated. For those of you not comfortable with multiplying fractions, it's really not too bad. Here is the simplest way to solve this. Any whole number, literally any of them, can be turned into a fraction by giving it a denominator of 1. Because remember, fractions are division problems. 10 divided by 1 is still 10. That's why this works. And then we've got the very simple task of just multiplying this through. 5 times 10 is 50. 6 times 1 is 6. And if you're comfortable with those multiplication facts, you're probably already figuring out, well, 6 can go into 50 8 times, and that would be 48, so I'd have 2 left over. So 8 2/6 total miles in that 2-week period, but it did say simplest form. And now we can come back and turn that 2/6, divide them both by 2, and we get our 8 1/3 would be our final answer on number 12. And now we can slide on down to number 13, which looks horrifying with all these fractions and whole numbers and multiplying and inequalities, greater thans and less thans. But the key here is simply knowing what happens when you multiply by 1. When you multiply by 1, it stays the same. 10 times 1 is 10. 47 times 1 is 47, and so on. And you also already know if you multiply by more than 1, your answer is going to get bigger. But then logically, that means if we multiply by less than 1, our answer gets smaller. I told you at one of our first practices that these questions aren't just testing your ability to be able to find an answer. Sometimes it's testing your understanding of what's really going on here. Because the key on this one is we don't actually have to multiply any of this out to figure what ones work and what ones don't. We can use those basic properties of multiplication, that when you multiply by 1, your product stays the same as the other factor. When you multiply by less than 1, you're going to get something smaller than you started with. And if you multiply by more than 1, you're going to get something greater than what you started with. So as we go through these, we don't actually have to multiply it out. We just have to understand multiplication properties. So 3/8 times 5/5. Well, 5/5 is 1. So that means I would get 3/8 as an answer. Well, that's not going to be more than 3/8 because multiplying by 1 stays the same. So A is gone. 4 times 3/2 should be less than 4. Well, 3/2 is more than 1. So I know if I take 4 times more than 1, I'm going to get more than 4. That doesn't work. So that one's out. And then I take a look at C. 4 times 2/3 is less than 4. We're just deciding if it's true or not. Well, 4 times less than 1 is going to get me something less than 4. It doesn't actually matter what the answer is. We just have to decide, is it less than 4? It would be, so C definitely works. On D, 6 times 4/3, is that greater than 6? Well, 4/3 is greater than 1, so 6 times anything greater than 1 is going to get me something bigger than 6, so that one works. And then 6 times 3/4 is greater than 6. Well, 6 times 3/4, that's less than 1. So I'm going to end up with something less than 6, not greater. So E goes bye-bye as well. C and D would be the correct answers on number 13. As we come down to 14, we just had a couple of very tricky fraction problems in a row. They're really a trio of tricky fraction problems. Then they give us a little bit of a brain break here. It's still got a fraction in it, but this one's much simpler. Number 14, the basketball coach ordered 9 pizzas to feed his players. Each pizza was sliced into sixths. How many total slices of pizza were purchased? Well, that one's not too bad. That means one pizza gets you 6 slices. This is one of those ratios. So 9 pizzas, if I've got 9 times as many pizzas, I'm also going to have 9 times as many slices. So 54 slices, and boom, we're done. That simple, that quick. No problem there. And then number 15, this is the last one we'll cover in this video. Susan plans to add a patio to the outside of her home. Using the diagram of Susan's patio, what will be the area of her new patio? So area is like filling a flat surface. So she's looking to cover this whole flat rectangular area. And to find the area of a rectangle, it's length times width. And those are often written in cursive when you see those written, just because a lowercase l when you print looks too much like a 1 and could be confusing. So we just have to multiply these two numbers together. So 6 7/10 times 4 9/10. And if you aren't super comfortable multiplying decimals, here's your strategy. First step, pretend the decimals aren't even there. Pretend it's 67 times 49, and when you multiply all that out, you should have gotten 3283, 3,283. Now I know that's not our final answer, we still got to deal with the decimal, but if you pretend it's not there and multiply these numbers like you normally would, these are the digits that you should have gotten in your final answer. From there, you've got 2 different options. One way is use your estimation skills. 6 7/10 is about 7. 4 9/10 is about 5. So I know I should get something somewhere around 35 square meters, which means the only reasonable place to put the decimal is here between the 2 and the 8, because that gets me something just a little bit less than 33, so that fits my estimate. Another way you can figure out where the decimal belongs on this is just count your decimal digits. I have 1 decimal digit here and 1 decimal digit here in the problem. If there are 2 decimal digits in the problem, then there should be 2 decimal digits in the answer as well, starting from the right. So 1, 2, put our decimal in, and we've got our final area of 32 and 83 square meters. Area is always in square units. That's literally never going to change whether you're solving that problem right now as a 4th or 5th grader, or you're solving an area problem as a construction foreman 30 years from now. Area is always going to be in square units. So we're going to wrap this video up with the first 15, and then there will be another video probably right next to this one in a math team playlist for 16 through 30. So thanks for watching, and remember, you can always go back and re-watch the strategies on all of these if there was something that we went a little bit too fast on.